So today we're going to try to wrap up our study of Chapter 10 and statistics. We've talked about our categorical graphs and our numerical graphs. And the numerical graphs we've looked at so far have been our box plots and our dot plots and stem and leaf plots. We talked a little bit about histograms, but we're going to take a little more time to look at those histograms. And then when we meet on Wednesday, we'll go ahead and use Desmos to do those creations for us as well. A histogram is kind of like a stem and leaf plot, but turned over so that we're looking at vertical leaves. The difference between the stem and leaf plot and the histogram is that with a stem and leaf plot, the leaves, you can see those individual data values, and with a histogram, we lose those values. We look at an interval of values and kind of get an idea about the data, but we lose the actual numerical values. I have two different histograms drawn up here. The first one that we're looking at is the body mass index for a sample of 101 individuals. So along the horizontal axis, you can see the BMI values, and the vertical is telling us how many individuals have that particular value. So like the stem and leaf plot and the box plot, the histogram, we can easily identify, the low end. So our lowest values look like we would have a value in that 18 BMI, and the highest value looks like a 31 BMI. Again, we don't know exactly what the values are because it's the number inside that interval. So it looks like from 18 to 19, we would have some individuals in there, but they could be decimal values as well. We do see that we have a mode. The mode's going to be the tallest bar there. So it looks like our mode is happening from the 24 to 25 BMI range. One of the things we like to notice about a histogram is how the bars or the data values are distributed. And so a lot of times what we do is we try to draw a curve that kind of matches our data here. Oh, and my curve does not look so good. But what you want to notice here is that for this data that we're looking at, it looks like the curve actually makes, we talk about it being a normal bell-shaped curve. And so it looks like we have this peak that's happening pretty close to the center of our data, and it's just one peak. And then the bell shape, or what we call the tails of our graph, are pretty evenly distributed. So the lower part of our bell-shaped curve is called the tail, and then the high point is going to be our peak. And here, because that peak is in the middle and the tails are about the same size on both sides, we would say that this is an approximately normal distribution. So we would say approximately normal curve. If we move over to the age of the Best Actress award winners, we can see that the horizontal axis is ages, and the vertical axis now is looking at the percentages of actresses. We can see that the youngest actress age interval we had was that 20 to 25 age bracket, and it looked like we have maybe around 7% of actresses are in that 20 to 25 age bracket. We can see that we have some extreme values in that 80 to 85 age bracket. We have 1% of our actresses falling in that range. And we also have some gaps from 50 to 60. We have a gap, 65 to 70, and 75 to 80. So we can pick out all of those things, and then we can see that our tallest bar is the 30 to 35 age group, which we could say is like our mode for this data. It does look like our data has one peak, and it looks like that peak's happening to the left, and then we have this longer tail. So if I go ahead and try to draw in my curve, it looks like I have this peak that's way over to the left, and then this long tail to the right. And so we name our curve by the tail length. So in our normal distribution, when the two tails were about the same, we say it's normal. This one here is going to be skewed, so we don't have our peak happening right in the center. And we're going to say that it's skewed to the right because the tail is much longer to the right. We can see here that the tail length here is much longer than it is on the left-hand side. So we would classify this as right skewed. So anytime we have a histogram, even a stem and leaf plot and a box plot, we can look to see where the median or the large majority of the data is, and then we look to see the tails, or in the box and whisker plot, it would be our whiskers. We want to see how far those data are off from that median value or that modal value. And we can name the skewing that way. So again, normal distribution means you have a peak in the middle and the tails are about the same on both sides. Skewed right means I have a longer tail on the right-hand side, and a skewed left would be a longer left tail. What we're going to also move on is we had talked about the measures of center and the measures of spread. The measures of center that we looked at were our mean, our median, and our mode. And the measures of spread that we have looked at so far have been range and interquartile range. We're going to take a look at something called the standard deviation. The standard deviation matches up really well with the mean because standard deviation means we're trying to figure out how far our data deviates, so difference, from the mean. So we're going to be calculating the average of how much the values differ from the mean. So if we are trying to calculate the standard deviation, step number 1 is going to be to find the mean of this data. So pause for a second, pause this video for a second, and go ahead and calculate your mean. So you should have found the mean value to be 74.14. I just rounded it to the nearest hundredth. So that's our step 1. We're going to go ahead and find our mean value. And then in step 2, we're going to go to this second column in our chart here. And what we're going to do is we're going to take the value minus the mean. So that x bar is our mean. And what we're going to do is we're going to take each value and subtract it from the mean. So for example, we're going to start off by taking 71 minus 74.14, and that's going to give me a mean value of negative 3.14. And I know if I have another 71, it's going to be that same value, negative 3.14. I'm going to do 72 minus my 74.14. I get negative 2.14, and we're going to continue all the way down. So go ahead and take a minute or two to finish up that. So I went ahead and calculated all those differences and put them in. So make sure you agree with the numbers I have there. So that was our step 2. And then what you want to notice is that if you were to add up all the values in this second column, they would come out to be approximately 0. And so it's not really helpful for us to take the average of the differences because we have some negatives and we have some positives. So there's 2 solutions to this. One of the solutions is to take the absolute mean difference, where we use the absolute value. But the more commonly used method is to use what we call the standard deviation. And that's where what we do is we take those differences and we square the differences. That eliminates those negative signs. And then we can go up and do that average and then undo the squaring later. So we're going to go ahead with our calculation of standard deviation, and our step 3 is going to be taking that difference that we just found. So this x minus x bar here is really what we had in column 2. So column 2 squared. So it's just our differences squared. So for example, what I'm going to do is I'm going to take that negative 3.14 and I'm going to go ahead and square it. And when you square a negative number, if we have it in parentheses there, it's going to become positive. So when I square my negative, it's going to give me a positive. I end up here with a positive 9 point, I'm going to say 86 because I'm going to round it off. If I square that negative next negative 3.14, I get a 9.86. When I square the 2.14, it gives me a value of 4.58. I'm just going to round to the nearest hundredth. That 1.14 squared is going to give me a I'm going to say 30 because I'm rounding it to the nearest hundredth. So I have quite a few of those 1.30s. And then I'm going to ask you to go ahead and keep on going. So the column 3 here that we have should be all positive values. We're just squaring the values we have in column 2. So take a minute to go ahead and do that. Okay, so after you went ahead and squared up that every value in the second column. You should have a column similar to my column 3. And now when I add up those values, because they're all positive, I'm going to get a sum of 57.72. So we're not done yet, but we found our total of our squared deviations. So we're getting close to what we need to do here. So after we found our squared deviations, what we're looking for is we're trying to find the average each value differs. So what we're going to do here is we're going to, in step 4, I don't know why it just moved. In step 4, we are going to go ahead and calculate the average distance, or the average of our values here. But this average is going to be a little bit different. So what we're going to do is we're going to take the sum of our squared differences, and this time we're going to divide it, instead of just by the number of items, we're going to do one less. This here is going to help us balance out with whether it's sample data or population data. Typically when we're doing sample data, we want to just, because we're not getting the full population, we're just taking a sample of it, we're going to try to balance it by doing this n-1 value. So what we're going to do right now is we're going to take that 57.72 and we're going to divide it by 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 minus 1. So here we're really going to be taking our 57.72 and we're going to divide it by 1 less than what we have. We're going to divide it by 13. When we take that average, that's going to be called our variance. So the variance, we're not at our standard deviation yet, but our variance is going to go ahead and equal that 57.72 divided by 13. And our variance ends up being a value of 4.4. And then finally, in step 5, we can calculate the standard deviation. I'm going to use SD to represent that. The standard deviation is the square root of that variance, that 4.44. So we're going to go ahead and take the square root of that value. And it looks like our standard deviation for this particular problem is 2.1, which tells us that the values we have here for these heights vary from the mean. The mean was 74.14, vary from the mean on average by 2.1. So that standard deviation is on average how much the values vary from the mean. So we can say on average these values or these heights are 2.1 units or inches, whatever our measurement is, from the mean. And that's the 5-step process we use to calculate the standard deviation. We'll look at another example here in a minute. So moving on, we've talked a little bit about our graphs. We've talked about line graphs, which show us kind of almost like a X and Y axis, but over time. So it's going to tell us how some things change over time. We talked about bar graphs and how they can compare values and make individual comparisons between categories. The circle graph is a good comparison to the whole because we can see what percent of the whole is being represented. Line plots and dot plots work better when we have smaller sets of data, and with both plots we're able to see those individual data values, so they're super helpful. The scatter plot is somewhat similar to the line graph. The line graph is like a kind of a connect the dot kind of graph, where a scatter plot we're going to plot all of our points and then look for a trend. So we have some scatter plots here that are showing us some different or two different variables that we're looking at. Sometimes we look at things like height and weight. It could be things like pay and satisfaction. So it depends on the variables that we are trying to make a comparison, but we're trying to look at things. So it might be hours of sleep and hours spent on social media. It could be hours of sleep and how much exercise you get. So it's two variables you're trying to see, is there any relationship with. Here we have number of falls and RN vacancies. So looking at hospital data. And so what we want to look at is just how closely the data falls to a line. And so typically what we do is we go ahead and graph our data points, and then we look to see if there's something called a correlation. And the correlation is like, what is the data trending? Does it look like it's linear? Does it look like it's curved? A negative correlation is when it looks like the points are going in a downward direction. And those that example would be seen here in this second scatter plot. We have data is going in a downward trend. In this fourth one, we have a downward trend, but they're a little bit more scattered points. When we look at a positive correlation means that we're looking at these data values, and when we try to draw a line to them, it looks like they're going upward. So positive or negative is just the direction that the line that might kind of follow the trend of these data points goes in. The other thing we look at is the strength of the correlation. How close to a line are the data points? And the strength of the correlation goes from a value of -2 to +1. With 0 being the weakest, -1 is a very strong negative correlation. A +1 is a strong positive correlation. So if we have data points that are getting really, really close to forming a straight line, we should be looking for a value between at -1 or +1. If it looks like they're pretty scattered, but they're definitely going in an upward trend or a downward trend, that's going to be more of a moderate correlation. And then if the data points form a curve, or if they're all spread out all over the place, then we would say that there's no linear correlation. That would be at a 0. So what we're going to do here is we are going to take a look at this scatter plot and then decide, once we plot these points, what type of trend we think we have, and then we're going to come up with our line of best fit. So take a moment to go ahead and graph these data values on the axes I have here. The horizontal axis is going to be number of classes missed, and the vertical axis is going to be grade in the class. All right, so I went ahead and graphed these data points. I can see that the data points are really kind of up high on the top part of my graph. It does look like the data points are kind of scattering around a line, and it looks like the data values could be going in a negative direction. So what I'm going to do here is I'm just going to go ahead and draw in a line that I think is going to fit kind of close to this data here. So let me see if I can get a line going here. And I'm going to draw it in black here, and I'm going to go with a trend line like this. Not very straight. So it looks like from the trend line that I drew, I have 1 point below. I do have a couple points above. Actually, let me go back and retry that one. Let's go back and draw in a better line. Let's draw it going through. Like that. So now it looks like I have a better scattering. It looks like I have 1, 2, 3 points above, 1, 2, 3 points below. So it looks like as the x's increase, the y's are going down in value. And so it looks like my line is going to have a negative correlation. And then what we want to do is we want to come up with a way to describe this particular relationship that the lines have. And so we normally try to come up with a regression equation or just the equation of a line. So what I'm going to do here is I'm going to pick some values. I'm going to start off here with this initial value that I had started with here, which was 0.98. So that's going to be one of my points, 0.98. And then the other point isn't a point on my actual graph, but it looks like my graph is going through this corner right here. And that corner right there looks like it's at the point 4, 80. So 4, 80. And so what I want to do here is I'm going to try to find the equation y equals mx plus b. And really what I need to do is, because my value is at 0.98, I already know that it's crossing the y-axis at 98. So I know my b value is 98. And what I need to find is my slope. So remember, to calculate my slope, I'm going to go ahead and take y2 minus y1 over x2 minus my x1. And here I can say x1, y1, x2, y2. So go ahead and calculate your slope and we'll come up with our equation of our line. So go ahead and pause that for a minute and figure out that slope. All right, when we went ahead and did that calculation, it looks like we should have ended up with a value of -9/2. So the equation of this line is going to be -9/2 is really -4.5. So -4.5x plus 98 is going to be the estimated representation for this line. So we went ahead and did that. And then we can go ahead and use this information to make some predictions. So in number 6, it says use the prediction for someone who has missed 3 days. So we can go ahead and say, okay, if my student had missed 3 days of school, I would expect that their grade in the class would be -4.5 times the 3 days plus 98. And their grade in the class would be .85. So I would expect an 84.5% for that student. And then we can do the same thing for 10 days. So if the student had missed 10 days, so y equals -4.5 times 10 plus 98. So -4.5 times 10 is going to give me really 45, a -45, and I'm going to add on that 98 to it. So the student would end up with a 53% in the class. So that was going ahead and creating that scatter plot, coming up with the line of best fit using our best approximation. We actually have Desmos and we also have Excel that can come up with an even better approximation for us, which we'll take a look at on Wednesday. And then we can do some estimates. Some things that you want to think about with your estimates is that when we are estimating values in between the data, so when I was going ahead and looking at this 3 days missed, notice that the number of days, 3 days missed, was inside the data values that I had graphed. So my data values that I graphed for classes missed, if I look over here, it went from 0 to 6. So because the 3 was inside, because 3 was in between the data values that we were looking at, we would call this approximation interpolation. We're interpolating the value or the approximate. So interpolation, or we interpolated the values. When I look at something like the 10 days missed, notice that 10 days, because my range of values from the chart was from 0 to 6, 10 days is outside of the data values. So 10 is outside, 10 outside of the data values. We call that approximation extrapolation, or we're extrapolating. So to extrapolate. So extrapolate means outside of the data values, and when we interpolate, it means that we're looking at in between the data values. So those are two other terms we have. All right, so what I want you to do as your last little practice for the class today and for working together, what I want you to do is we're going to take the grades in the class. So you see that we have the grades in the class here, 93, 68, 93, 68, 91, 85, 98, 75, 96. What we're going to do with that is we're going to go ahead on this next page and find the standard deviation for those values. So we're going to go ahead step by step, and again, I'm going to let you pause and calculate as we go. So when we go to this next page, we're going to be looking at those particular data values. All right, so I wrote down the values for those test scores. Those were my X values. And remember, what we're going to be doing is we're going to be calculating the standard deviation. And so when we calculate the standard deviation, we're trying to figure out how much the data varies from the mean, which we call X bar. So remember, step number 1 is for us to go ahead and find x bar, or find the mean value. So go ahead and take a minute to calculate that mean value. Okay, and I ended up with an 86.57. So then step number 2, remember, is to go ahead and find each value's difference from the mean. So I'm going to go ahead and take 93 minus 86.57 and write down that value. And then I'm going to go ahead and take 68 minus that 86.57, write down that answer. And we're just going to continue down, so it's going to be the value minus the mean. So go ahead and complete that chart. Okay, so I went ahead and found each of those differences, and then remember, with standard deviation, what we want to do is we're going to square those differences, because if we were to add up our column number 2, we would end up getting a value of 0, which isn't going to be really helpful to tell us how far the values differ from the mean. So in step number 3, what I'm going to do is I'm going to take the differences that I just found, and what I'm going to do is just square them. So for us, what we're going to do is we're going to take that 6.43 and we're going to go ahead and square it. 6.43 squared is going to give me an answer of 41.35. And then I'm going to take that negative 18.57, and when I square negative 18.57, it gives me a positive value, a pretty large number, 344.84. I guess I should have said 0.84 if I'm rounding it to the hundredths. All right, and we're going to go ahead and continue down this list doing the same thing, 4.43 squared, and so on. So take a moment to finish up those squared values. All right, so I went ahead and filled in that chart. I also corrected that top value. When I squared that 6.43, I rounded it incorrectly, so 6.43 when we square it was 41.34. So I went ahead and squared all those values, and then notice step 4 I started because I needed to get my total. So we're going to add up column 3, and remember in step 4, what we're going to be doing is we're going to be calculating what we call the variance, and the variance is going to be the average, but it's going to be the sum divided by n minus 1, one less than the number of values that we have. So in this particular case, our variance is going to be that 761.68, which were all the values I added up. And I have 1, 2, 3, 4, 5, 6, 7 values, so I'm going to go one less. I'm going to divide by 6, dividing by one less than that. So then that will give me my variance, and we're really close to being done here. So 761.68 divided by that 6, that's going to give me 126.95. And then finally, to get that standard deviation, what we're going to do is we're going to take the square root of our variance, which was the 126.95. So we're going to go ahead and take the square root of that value. And it looks like our standard deviation here is going to be 11.27. So remember, in the previous one, when we were looking at those heights, our standard deviation was about like 2.2 or whatever. And then in this particular case that we're looking at with these test scores, our standard deviation was quite a bit larger. It's 11. So the larger our standard deviation is, the farther the values are from the mean on average. So when we have values that are really close to the mean, our standard deviation is small. And when we have values that are further away from the mean, it's going to make our standard deviation larger. Again, standard deviation is just another way that we can measure the range of our scores. So that is where we're going to end here. You do have a homework assignment that's going to be moving on into the next chapter, which is going to begin some geometry work for us. I do have, or on Wednesday when we meet, we will go through some practice problems where we're going to calculate the standard deviation again, create a scatter plot, and we'll take a look at how we can use Desmos to help us as well.